Thank you. Okay, so today we are going to talk about the geospatial processing for machine learning engineers. Because I know this is not a hot topic like it could be artificial intelligence, but this is very interesting because this is a different way to understand the data. We always take a look at the static data, sometimes at time series, but we don't really get to the point in which we analyze the geospatial data, which is also a different way in which we should treat the data. Okay, so this is what we are going to do today. This is the overview. First, we are going to have a quick introduction around 20 minutes in which we are going to talk about how the geospatial data looks like, and then some real businesses and some real use cases that we can have out there in the real world. And then we are going to head to the geographical data. We are going to understand the types of data that we are going to work with. We are going to take a look at how to visualize it and how to work with this data in the end. So this is where I speak. However, I'm going to try to hype this topic. However, I would like to have some interaction with you. I'm going to ask some questions. Feel free to answer. If you don't want to answer, it's okay. And then this is the real world. This is where we are going to code, all of us. So I can see that everybody has a laptop. That's okay. We are going to code together and we are going to use Google Collaboratory. Okay?
Sorry to interrupt.
Yeah.
Do you have it set?
Oh, yes. Everything is in Moodle. You can download it now. So we don't, but we have plenty of time. Okay. So first of all, the geospatial data in general. When we talk about geospatial data, we usually think about three different features that make the geospatial data something different. I'm thinking about three features, probably the main important features of geographical data. What features do you think geographical data should have? And one is very obvious. Location. Exactly. First type of information that we want to have is the location of something. And where to locate something in the Earth is what we use the coordinates for. So latitude and longitude. This is the way we locate shapes, objects, or whatever that we want to locate, whatever that is geographically referenced, can be located within coordinates. So the first one, that was okay, right? Location. What other feature we can have in geographical data? This is not that obvious. Perfect. Attributes information. So now that we know the location of something, I would like to know what is that. This could be characteristics of the objects. It could be if I have a shape of a polygon, it could be a hospital, a house, it could be a lake, it could be the ocean, or it could be events or phenomena. For example, I was a year ago, I guess you knew, but in the Canary Islands, a volcano exploded. So a lot of information, a lot of geographical information was used because it prevented people from being injured because they could forecast some way where the lava was going to flow. So it's very important in that sense also the geographical information. And what would be the last attribute that we may take into account? Time information. Because even though I said at the beginning that we have static data, we have time series, and then we have geographical data, but time and geographical data are also something that could work together. If we want to know the lifespan of the attributes, because all the data, even though it's located somewhere, it may change, because think about, for example, the mobility of the population. That's something that flows and could be very quick. But also the static data. We may want to know that something is going to be there for years, forever. Okay, so these are the three attributes that we are going to consider in the geographical information. And what can we do with geographical information? Well, these days, since the disruption of software, we have something that is called the Geographical Information System, GIS, which is a tool, that's an important word, just a tool to get insights of the geographical data. And with this kind of tool, we can discover, we can get knowledge thanks to the potential of the software that should be interactive, easy, explainable. That's what we would like to ask for this kind of software, the GIS. I'll let you hear the strict definition. GIS is a system of a computer software, hardware, data, procedures, and personnel. You can agree or not with that. I disagree personally, but I consider it only a software to manipulate, help, analyze, or present information that is tied to a geographical location. Okay, so it's not a map. It's not just a map. It's something that we may want to extract some information, some insights, like could be Google Maps, that is going to tell us where, for example, if we want to go from Moncloa to the university, where is the better road to get there by bicycle, and how is going to be the traffic. So this kind of insights is something that a map cannot give to us. It's something that only a GIS can do. And I would like to show, before answering this question, some examples of GIS. For example, this one, I don't know if you know it, World Weather Online, is a map in which we can see the weather worldwide. And with a really quick sight, we can know what the weather looks like in the whole Earth. This is a geographical information system, and it's a very cool one. It has, as you can see, different layers. So we have the layer, like the shape of the countries. This is one layer, and on top of the layer we have colors, which represent the weather, the temperature, and on top of that we have the wind. So we may more or less know how the weather is going to change in the world. Another example, this one, probably you knew. But in this one, we have the Earth, and then we have all the flights that are in the Earth at the moment, and where they're going and where they came from. Let's pick a random one. Nantes, Agadir. Okay. But a lot of information can be extracted from this. And I would like to show you another example, because I think this one, it's very interesting, because in this example, what we have is some area of influence and some data related to this area of influence about population living there, or their gender, or their age, or buildings that are constructed there. And this is a startup that was a spin-off in the university. I co-founded this startup. And in the second lecture that we are going to have next week, we may talk about more about this startup. And if you are curious about anything, I can probably answer that. But I introduce it now, but we will take a look in the future, okay, in the next week. Or another example, how the flu is spreading in the United States these days. Apparently, New Mexico is struggling, okay? Right. So is it clear what a geographical information system is? I think it's quite clear. So with the geographical information, not the system, not the software, but in general, the geographical information, we would like to answer this kind of questions, which are very difficult. If you consider, if you don't take the perspective of geographical data, where these things happen is something that it needs to have geographical information within the data. If we want to recognize patterns that are only there because they are located somewhere, we need to apply different operations to the data. It's not like working with time series. It's something a bit different, or clustering, or hotspots or disparities? Or why do they happen? Where they happen? That's something that we would like to answer as well. How does where things happen affect other things? It's no longer, I would like to show this. For example, this is a map in which I've included random data randomly distributed in this city. And this is the real data, which is distributed in the center. It's the number of people and the density of the people. So if you think about the histogram, they're exactly the same because we have the same number of blue and orange and red things. But they are not the same. These two informations, this one, we may want to retrieve some information based on the geographical information, which is something that we don't have if we just take a histogram. Okay, that's why it's important to understand that we have to treat it differently. And then where the things should be located, that's also optimizing routes, optimizing the traffic, optimizing how the people should move, or optimizing where we should locate a hospital. Okay, important stuff. So we are not going to get into specific details of the geospatial statistics because that would take quite longer. What we are going to do is we are going to learn today how to deal with the data, how to perform some operations with the geographical shapes and structures, not specifically the statistics. However, I wanted to point out that this exists and that we have to treat it differently. And if we have time the next day, I will introduce it. Okay, but it's a different step in the data science. Oh, I wanted to ask something before that slide. Where do you think geographical information can be applied? In which areas, in which businesses? Tell any, and yeah, transport, okay. Any other? Pollution, okay. Prevention of the pollution, perfect. Military, yep. Well, it's actually everything, okay. And telecommunications. It's if you are going to work as a data scientist, you most probably are going to find yourself working with your spatial data independently where you work. It could be in insurance, it could be transportation, humanitarian help, nautical, economics, disaster, crime, real estate, businesses, architecture, society, anything. So if you are going to work as a data scientist, which is something probable, you are going to work with geographical data at some point. It's not going to be your main job, but at some point you will have to use it. So today's lecture is going to be very useful for that, because now you're going to know how to deal with it. It's not going to be super new, at least. And now, well, the real businesses, I would like to share some of the, because these businesses, it's like a next level of abstraction. It's not only that I work in a hospital and I would like to know some geographical information about the probably people that is going to come to the hospital. Is that some businesses appeared on top of everything, like appear just working with geographical data. This is the case of Carto. Carto is a Spanish startup, and they just work with the geographical data. They have they are consultants, and they help some other people just with geographical data. That's how important this job is, or what I already shown, Picgeo, which is the startup that we co-founded, or Esri worldwide. This one is also the same. They provide maps. They provide any kind of tool that we may want to use in a GIS or when we work with data. Just for you to know that it's not only related to a lot of businesses or areas, but also some startups appear on top of that. And now some fun facts. And this is the last slide for the first part. This is Harold Samuel. Okay, this is the founder of one of the biggest companies in the UK, Land Securities. And when he was asked, what are the 3 features that matter the most when starting a business or buying a house, 3 features. What do you think he answered? What are the most important features when buying a house or starting a business? Location, okay, that's one.
I think intensity of parts or business and
The area, you mean, but that's related to location? But you mean population in the area or any kind of shops?
to extract the information of the area. Not
Mhm.
of the area.
Okay.
If there's a lot of parts, maybe it will be a more well-off population.
Yeah, okay, it's like welfare of the area. Okay. And the third one, what do you think? Okay, I'm going to tell you the answer. The answer, what he said, and he's super rich man, I think he was, is location, and then location, and then location. So that important is. I want to hype it. I told you I wanted to hype the topic. And then another thing that is very interesting is that if you specialize in this topic, the salary is higher in average, at least in the States. That means that being a data scientist is very good, but being a data scientist specialized in geographical data is well paid, even more. So that's a topic that you may want to take into account. Okay. All right. Do you have any question to this point? Okay, then we are going to jump to the next part of the introduction, which is the real world. Now, we want to work with the geographical data. This was only the hype. So the first thing that we want to know is the different shapes, different objects that we are going to consider in geographical data. These are points, lines, and polygons. Point, 0-dimensional information. It has no dimension. It's a singular point somewhere with some information, but no dimensions. Lines, 1-dimensional information. Could be a road, could be something that doesn't have area. And the polygon, by definition, it has area and it has to be closed, like this plus sign. It has to be closed. If some information has more than one of this, then we call it the keyword, multi-point, multi-line, multi-polygon. That is, if I want to define, I don't know, where trees are located in a hill, then I may define a multi-point. Or a multi-line if I want to have a highway with one direction and the other. Or it has 4 different buildings, I could define it with multi-polygon. Okay. And these are what we call the primitive vectors because are the simplest. There are more, but we are not going to get into that today. More like the point clouds. These are the case of the LIDAR, laser detections. This is when we have something like a drone or like a plane and detects a huge area defined by a point. So the plane would locate a uniform number of points in this barrier in this area and then define some kind of attribute. In this case, is how high these hills are or low. Okay, and then raster imaging, which is images in which each of the pixels have information. Like this case, each of the pixels we have colorized them, but this is a picture of somewhere in which blue means the sea, red means a building, green means a field. But each of the pixels. And that is also a different engineering topic. I mean, we can consider it in the geographical data, but it has its own field because it's so complex and it's closer to the image engineering. It's closer to the artificial intelligence these days that we cannot consider it like specific part of the geographical data, but it has its own name. It's very difficult to pronounce. Imaginary engineering, something like that. Imaginaria. Okay, so it has its own feel. It's quite difficult. This is something that in GTI they would do, for example. And there's another one that I haven't put here, which is when we have I forgot the name. When we have like a grid, like roads, we have nodes and graphs. Exactly. This is another thing that we may measure in the geographical data with geographical data, graphs, because as I said, in the graphs also we can measure time and flow, and that's something that we may model this way. But that's also another thing that is very complex. We are going to get only to the simplest one today. Now that we know that we have points, lines, and polygons, how do we input this in the computer? So we are going to take a look at 3 different ways. The first one is the WKT, well-known text. And this is a string of characters to define the primitive vectors. If we want to define a point, we just write point, latitude, longitude. Line, then line string, latitude, longitude of all the points that define the line. And polygons, it's polygon, latitude and longitude of the vertices. And the first and the last need to be the same because they need to be closed. Okay. And the multipoints is more or less the same with a different keyword. What is the problem of this kind of representation? I mean, it's the simplest. It's just writing in a string the name of the keyword and then the latitude and longitude. But even though it's humanly readable, it's a mess if we have a huge database with a huge, for example, a huge polygon. The polygon defining Spain, the shape of Spain, it has a lot of points. Imagine that string that's too big. Okay, and the other thing is that we can't have attributes linked to the geographical point, to the vector. We can't have them. I don't know if I have this point. What is this point? I have no idea. I would need to have some data somewhere apart from the point to know what that point means. Okay, so we usually use another way to save it. One is the Esri shapefile. Esri shapefile. I know this is Esri is a private enterprise, and I'm not into showing something that is private, but it's so much used that we need to know it. And the way Esri shapefile works is that they have 3 different files: SHP for geographical entities, that is points, lines, or polygons; SHX to index those, to link with the DBF, which is the attributes. But what is the problem? I mean, if I'm given something like this, yeah, one SHP file, one of this, and some others that are optional and that almost nobody knows, I have no idea what is inside. I have no idea what is this. I don't know, unless it has a name. Cities. Okay, cities. So what I would do if suddenly I have to process something like that, I would go to this website, Map Shaper, and then this is a soft client in which you can just drag and drop some file like that one, import it, and now you can have a taste of what is inside. This is how I usually work with shape files. And this tool is very cool because I can have a console here, and I can see what are the attributes of this data. For example, info. I can know that this is a layer Europe, it's a polygon, it has 54 records, I guess, countries. and I have the name. So I can even query it or filter it. Oops. Oh. Okay. So this is how I usually work with this. Another thing that is very interesting about this tool is that we can simplify the geometries, because sometimes we don't want to work with this kind of precision. See how precise these are. I mean, you can see that well, but it has every single point that I may not want to see. So I can simplify it so the SV file weighs less, it's less heavy. The problem is that if you simplify it too much, look how it's simplifying. You may remove some important information like Portugal. Okay, we don't want to do that. Or the islands. Okay, but just for you to know. This shape, I use it a lot. Every time that I have to work with geographical data, and you will have to, I recommend using it. Okay, so this is the shapefile. And the last one is the GeoJSON. Do you know what JSON file is? Everybody? You sure? Because last year, nobody knew. Just a quick recall. A JSON file is a way we can store information that is a structure that is independent of the language, the code language we used, and that has different types. Name, Mateo. So we can have string, age, number, 28, attributes, and this could be a array. So we can store anything. I may have saved this file in Python, and I may read it in C++. Perfect. So GeoJSON is an extension for that, in which I can have an extra field, which is the geometry. And it will understand what is inside. If we read it with something that understands GeoJSON files, then it should have always these fields, type, the coordinates, and link. This is optional, but we may have properties. Okay. So this is recommended. This is the way we should work. However, a lot of people use shapefile. I'm sorry, but we have to live with that. So, but we are going to work with this today, and every time that you need to save something that has geographical information, then use GeoJSON. Let's jump to another thing. You know that maps, they are a lie. They are not telling the truth, because when we have a spherical shape like the Earth, and we try to project it into a plane like a map, then by definition, we need to change the way we see it. We need to modify the way we see the things. Think about this head. This is the way we may see the head, but if we want to put it in a Mercator, that's the name, Mercator projection, exactly the same as a map, then look how everything gets, I don't know, disrupted. I don't know how to call it. Then I would like to show you one website that may illustrate this a bit more, which is the True Size Of. I would like to know, where are you guys from? France? Where are you? Spain? Spanish, everybody? Iran? Wait. What? Oh, okay. Sorry. Any other country? China? Okay. So this is how we are used to see these countries. But if we move them to, for example, the North Pole, then they start to grow. Okay, they look bigger than they should be. Okay. But the same, if we go to the equator, our countries are actually very small compared, for example, with Brazil. This would be just a state, a small state of Brazil, Spain, or France is more or less the same. Iran and China think they are bigger, but if you put them in context, well, yeah, like Brazil, yeah, more or less. But some others are very interesting. I don't know if you knew about this about Indonesia. Indonesia is huge compared to Europe. I mean, it's the same as the Atlantic North when we go to New York from Madrid. Did you know that? And it seems like very tiny islands there. Or the last example, I just love this. The Antarctica. It's, yeah, like small part of Africa. So maps are not true, and because they are not true, they are lying. We need to do something. We need to just know it. We need to know they are lying. So depending on the different projections that we are going to use, we may retrieve some data or other. Some projections are measured in meters. So for example, every country has a projection. A projection is defined by a number. This number is called the CRS. In the case of Spain, we have the 2062, and this projection is measured in meters. So if we want to measure meters in a map in Spain, we have to project our map using this number. I will tell you how to put this number in a geographical context, okay? For Europe, the same. For France, this one. However, some others don't use meters, and they use latitude and longitude. That is, latitude, the arc of the measure from the equator, okay, in a horizontal axis, and longitude, the arc measure from the Greenwich meridian, okay, but in a vertical way. So if we want to compute a distance in these angles, they are not going to, we don't know what is a distance of one latitude point. I don't know. I know Madrid, for example, is in 43 latitude, and longitude is -3. This is the same as saying 3 west. Okay, this is coordinates. Madrid. What happens? What happens? Where do I go if I go to the 42? Cuenca? Catalonia? No idea. No idea. But what if I tell you that based on that reference system, the Spanish one, we are in the point, I don't know, 1 million. And I move 100 kilometers to the east. Then I know where I am. I mean, I can measure it, or more or less I know. This is more insightful. Oh, sorry. So every time that we want to measure area or distance, make sure that you are using a projection that is measured in meters. Every time that we want to locate something, make sure that we are using latitude and longitude. And if you mix for example, two data sets, one with one projection and one with the other, and you think they are the same, it's going to be a disaster. Okay, super important, this part. And another thing I would like to say before starting coding, we have 10 minutes this hour, okay, is that what we are going to do today, the step 0 would be using Map Saver. But we already knew, okay? I already showed you. The step 1 of a, let's say, geographical data scientist, the career, the things that we should learn is using QGIS. And then the step 2 is using GeoPandas. Shapely, and any kind of visualization tool, let's say Plotly. And then the step 3 would be anything, like no limits. It could be creating your own web app, like we did when we co-founded, or create your reports or whatever, or any kind of desktop app. So what we are going to do today is in the step 2. This is too basic for, I think, today's class. QGIS is a desktop application, this one, in which we can work. This is a GIS, but it's a heavy one because I install it, and in which we can take a look at the data, create lines, or add some more information to this map. But we would like to do this programmatically, coding. And for that, we are going to use to be in this step. And this one, it's up to you. If you liked what you did, then you can do your own web apps or whatever you want to do. Okay. But this is the idea. Today we are going to code, and we are going to use these libraries to work with geographical information. Okay, so you may have noticed that GeoPandas is very close to pandas. Do you know about pandas? Of course you do. So it's exactly the same, but it has some inbuilt functions that are specific for the geographical information. Okay, then, well, this is the way we can install it, because it's a bit tricky. If you don't install it, installing this first and then installing this later, it doesn't work. I don't know why. Then another library that we are going to use is Shapely, and this is for creating geographical entities, points, polygons, and lines. So we need to use it instead of using QGIS, which would be one click, and then I can have this line. This is how to do it programmatically, okay? How we can code it. And then Plotly is the way that we can visualize the map. There are a lot of different libraries for visualizing maps. I like Plotly because it's interactive, even though it's not meant for maps specifically. If you want to use a different one, you're free to do it. Today I'm going to show a bit of this, but I'm not going to get in much detail on this. I'm going to get in details on this and this one, because this is more up to you. How do you feel comfortable? Maybe you feel comfortable with a different one, and it's perfectly okay if they have a way to show a map. Okay. And then this is the last I would like to introduce. This would be in this step 3, which is Mapbox. Mapbox is a they provide a way to work with a map. I mean, they provide you with maps that you can publish on the internet for free. That's why. So if you want to create your own web app, for example, you may want to look to take a look at Mapbox, because it's like, imagine Google Maps. It's a map provider for Google, and Mapbox is a free option maps providing. Okay. Usually, instead of using the Google data, they use OpenStreetMap. I just want you to. I'm throwing you names and these slides for you to know if you really want to study this topic. So OpenStreetMap, it's the same as Google Maps in the sense that we have information of shops, buildings, streets, traffic, but for free. It's made by people for people. So some groups in WhatsApp and in Telegram, they meet up and they tag things like, this is a tree and it's here. Everyone for free, for fun. So if you want to support them, OpenStreetMap. And that's all I wanted to say for this first hour. In the second and third hour, we are going to code. We are going to take a look at the Google Collaboratory. But now we are going to have a break. Okay. Any question? Any curiosity? If you want to ask anything, you are free to do it.
Do you use Plotly in your daily life, or do you have another preference for the front end aspect of showing for web app developing?
Yeah, web app developing. Yeah, for dashboards, this is something that we are going to talk about, but not next week, in a couple of weeks. How to create a dashboard with Plotly. Yes.
And do you recommend it?
I do. I like it. I feel it's very interactive. It's very intuitive. You can create an HTML file on the fly, and you can publish it, and it's interactive. I think, in my opinion, it's the best. But I mean, it's up to you.
Back in France, we are working with medical data, and there are a lot of ISO to follow for medical data. And I have seen that there are also ISO on geospatial data, and I would like to ask if you follow them in your day-to-day life or not.
Who? If I follow
the ISO rules for the data.
I don't know them.
Okay, so
Sorry.
because when we are back in France, they are very strict about ISO rule for medical data, for example.
No, I'm sorry, I don't know it.
And maybe in that case, you must think about the following standard. Yes.
Definitely.
Like I'm working for your application that doesn't care. Specific areas in the health sector. Because that's very strict. And also with the dashboard, one of the main issues when we use the dashboard, the data in the dashboard is published in the dashboard with the client, but the data is going to sell to a client. So we want to have privacy issues, then maybe you need another type of tools like the Power BI.
Definitely. But this is, if you want to pop, I guess you can make your own authentication method and then.
But it's not a problem, it's really a problem. Because sometimes we feel I have very nice way back, I can visualize the data, but this data just is extracted from somewhere, so you have a lot of problems.
That is.
Your nice app is built on sensible data.
Yeah, we can create dashboards with Plotly, but what I wanted to, I don't have it. Oh yeah, Plotly, you can have graphing libraries for that are connected with Mapbox, and you can create maps. We will take a look at what Coropath means later, but you can create maps with Plotly, and I like it, but it's a personal option.
Are these tools suitable for checking dynamic data? I mean, if you want to, for example, last year I was working in a GIS that was doing with a GIS team following system for trucks and buses from a country. Are these tools suitable for doing that, or in pseudo real time, or?
Oh, with real time, what do you mean? It's connected with an API.
Like a GPS antenna or something in a railway,
Okay.
and you get that information for a delay with 15 minutes delay or something like that. If you can plot, for example, a map with the location of each car or
yeah, got it. So I know in Power BI you can do it, but you have to have some kind of trigger. So if you store this information in a data warehouse or in a database in real life, in real time, then you have to trigger every 15 minutes, read it, and then plot it. But you can do it. I know with Power BI, but I'm pretty sure with Plotly as well. I don't know. I've never do it with Plotly, but I've done it with Power BI. Break time. Okay, let's continue. So please go to Moodle and download materials part 1, and then please upload it to your Google Drive account and open the this file, Introduction to GeoPandas Students. Tell me when you have it. And then we are going to run the first 5 cells in which we have to mount our Google Drive account, install the dependencies, which are not installed by default in Google Collaboratory. Okay. Do you have it as well? Okay. So the first thing that we are going to do, we are going to import the Spanish provinces data frame. We are going to do it with GeoPandas. We can use the read file exactly the same as in Pandas, but the difference is this is not a data frame. Oh. This is not a data frame. This is a geodata frame, and we have some other functions that we can use with this geodata frame. If we take a look, it looks almost exactly the same as a data frame. The only difference is that we have this geometry. We have this column, and it's mandatory to have this column in a geodata frame, because this is, since we are using a geodata frame, we need to have some geographical reference. And in this case, we are seeing every province in Spain, and it's the polygon that defines the province. But this is mandatory, okay? The other things that we can see, they are attributes. I don't even know what this means, okay? I know this is the area, but we can compute it from the geometry. The length, I guess, is the perimeter, but These are all the things that we are not going to use, and the name of the province. But the important stuff is that everything that you know with pandas, you can use it, but now we have the geometry in GeoPandas. So exactly the same as we would do with a data frame, we can plot it, and it has a map integrated in GeoPandas. So we can plot it using, for example, a C map, a color map related to one column, and this column is the area. So if you take a look at the legend, that means that in red colors we will see the provinces that has a bigger area, and in blue colors the provinces that has a smaller area. Okay, Madrid, Valencia, Barcelona, Cáceres, Badajoz. Okay? Based on this column, we can show the legend, or we cannot show it, and I let you hear some of the most important attributes. But this is exactly the same as pandas. This is what I want to point out. So, since this is exactly the same as GeoPandas, I would like to ask you if you can find, using just pandas functions, which of these provinces is the biggest and which is the smallest, based on the ST area SH column. You have 5 minutes for that. And you have to tell me what's the name. I'm going to do it with you. I don't remember how I did it. Did you find the solution? Almost. Oop. Oh. Which is the biggest province? Badajoz. And the smallest? Melilla. Correct. Correct. So you've seen that we can do exactly the same. Okay, that was the idea. Now we are going to include one extra plot. This is a region of interest. If you take a look at it, it's just a triangle. Okay, but this triangle, if you take a look at the axis, it's located in Spain. So this triangle in the coordinate reference systems that we have talked before, it's somewhere, and it's metric. It's the metric. This is latitude and longitude. Okay, this could be meters, but in this case, it's latitude and longitude. So we can plot it together with the Spanish map. We can plot it in different plots, or if you put to get a figure subplots and you get the axis and you put the axis in the same axis for both, then you are going to have something like this, which is a triangle on Spain. Okay. This is to illustrate the idea that we may want to create some polygon or some figure or something and put it somewhere in the world, because we may be interested in something. For example, if we had a river or something like that, when we could plot it on top of Spanish territory. So we will have like layers. This is the same idea as when we work with Photoshop. Have you ever worked with Photoshop? We have layers. So same idea. We have to think in geographical information also like layers. Exactly the same. If I have the capital cities, I can plot it on top of everything. And now I have points. Okay. These are actually, they are not the capital cities. If you take a look, Barcelona, for example, they should be located in here, but this is the centroid, center of mass of each of the polygons. We will introduce that concept after, but just for you to know now. Okay, so if we can do that, then, and also we know which province has the biggest area, I would like to ask you to paint this province on top of the Spanish territory. And the Spanish territory should have, for example, a blue color, and then this province, Badajoz, should have a red color. Based on what you have done already and on this idea of putting layers, put Badajoz on top of everything. Can you do it?
It's difficult to see Melilla.
Yeah, if you want to draw to paint Melilla, Melilla is a city located in the North Africa here. So yeah, if we paint it, it's quite difficult to see. There it is. Okay, got it and got the idea? We have to think about maps, about plotting maps this way. We can point out, we can illustrate things just by putting on top of the other things. That's a very important idea. Then let's take a look at the coordinate reference system to think about the projection of the map. So every data frame have one CRS, one coordinate reference system. You can find it by using CRS attributes. You can see we have the number 4258, and if you recall, this is the number of it stands for Europe, and the units are latitude and longitude. But the region of interest has a different one. This is for the world, not just Europe. Okay. So what we have done, even that we have put it on top of Spain, this is not very correct because it has a different CRS. So probably this triangle should be located somewhere in Spain, but not exactly like that. Probably very close because the CRS for Europe and the CRS for the world, they are not that different. But you will see that if we mess up with a different CRS that are very different from one from each other, they are going to be very horrible. For example, if we change the CRS using to CRS function to something different, we are going to change the Spain, okay? This is for Spanish CRS, but now take a look at the units. We are using meters. So if we want to measure distances, the distance from Madrid to Barcelona, we would like to use this map because otherwise we would measure the things in latitude, longitude. But now we can measure in meters. And the zero, it's here, somewhere in the sea. Every country has a zero somewhere, wherever they like. For example, France has the zero. We're going to paint France, Spain with the France CRS has its zero in León here. Because that way they can measure the distances in France more easily. The same way that we have it in the sea here, they have it here to measure distances in France. But the important thing that you have to take from this is that the units are different, meters. So if I want to calculate the area of Madrid, now I can do it. And it will have some area in meters, in square meters. I couldn't do the same with the latitude, longitude. And what happens if we use a very far away country like Malaysia? It's upside down. Why? Take a look at this map. How would you look Spain from this perspective? Like this. Okay. That's why we need to be sure that we are using the CRS correctly. Otherwise, we can mess up a lot. This is not how we are used to see Spain. This is correct, but I mean, all right? That's why. Oh, I answered the question. Sorry. All right. So now I'm going to talk about the overlay function, which is a function specific for GeoPandas, in which we can perform functions specific for geographical data. Okay. In the second part, in the second script, we are going to take a look at all the functions that we can perform. This is just introduction. We can perform an intersection. So since we had our triangle, we can perform the intersection and get the Spanish provinces that were underneath the triangle. Okay, this is to introduce it, that we can do this kind of operations with the geographical data, which they may seem very obvious, but we need to know how to do it. And very important, if the CRS is wrong, like in this case, do you remember Spanish provinces had a different CRS than region of interest, then we are going to have a warning. Take a look at these warnings because they are important. This should be an error, not a warning, in my opinion, but it's a warning. Don't take it like, oh, warning, I can forget about it. No, important, ojalá. If they are the same CRS, then you won't have this warning. But it's an important thing. Then we can also compute some geometrical computations based on the geographical information. One of them, and very important, is the area. So if we have area, if we have a polygon, we can compute the area. But remember the CRS. This area is computed in latitude, longitude points. So it makes no sense to have 0.13 latitude. So we change it to meters, and then we can compute the area. And then we know that the area of province 0 is this one, the area of province number 4 is this one. But again, on the same idea, you see that I'm talking all the time about the same thing, but I want to be sure that this is in your head. Okay, this is in meters, so that's how I compute it. I can keep it in my data frame in a new column called area, and now this area is in square kilometers. Right. So I know the area of each of the provinces that were underneath, that were below the triangle. Remember? I know the area of this one. This is Madrid, so it's not the full area of Madrid. It's a bit less. Guadalajara. Okay. Is that clear? Any questions on this? So we have, yes.
So when you just showed the geodata frame for provinces in ROC.
Yeah, in region.
The geometry, the column that changes is the geometry column. All of the rest should stay the same.
Exactly.
And that column, the regions are defined as polygons.
Yes.
So what is changed are the vertices that are cut off.
Exactly. Exactly.
And that is done.
Yes. Yes. Now we can save it. As you remember, I put some emphasis on using GeoJSON. It's that simple. We can export it using to the function to file, and then set GeoJSON as the way to save it, the engine. And then it will. You can keep this new data frame with the geographical information in a GeoJSON file, which is also human readable. And then we have some student work that we are going to do now. First, please find the province of Barcelona and plot it. I want to recall that the name of the provinces come in a column called rótulo. Sorry. And please call the variable Barcelona. Capital letter, please. Wait. Got it? Okay. So now we are going to work with Barcelona province. And we are going to create our own primitive vectors, our own shapes. We are going to use Shapely. Oh, I erased it. We are going to use Shapely, which is the library that we can use to create polygons, points, and line strings. The way to do it is that from geometry, we import polygon or line string or a point, and then we pass the latitude and longitude of the coordinates of the polygon where we want to define the polygon. Remember that the first and the last should be the same. So now we have created our own polygon. You can see it's there. Look that I haven't printed. In Google Collaboratory, you can just put the variable and it will understand it's a geometry, it's a shape. We can introduce this shape in a geodata frame, and we do it like this. We declare a new geodata frame, which it needs to have the field geometry, and we have to input it as a list. Okay, that's why we put this thingy. And then the CRS, you have to define it. Otherwise, it will take a random one, and that's crazy, okay? So this is the CRS for Spain. Now we can plot it using geodata frame. Okay. But I wanted to plot it. Plot both. Sorry. Okay, let's do it. Plot both geodata frames in the same figure. That is Barcelona plot. So we have to define the figure. How did we do that? Oh. And now what you can see, I mean, I tried to create the city of Barcelona on top of the province of Barcelona. And I made it a square, okay? But more or less the metropolitan area is over here. That's the idea. We have created it with Shapely. We have used geodata frame to put it all together, and we have used geodata frame to plot it. And we have used two layers, province behind, city on top of it. And we could do the same with the river. Now we create a line string. We call that a river. We put it in the geodata frame, and then we can plot it the same way we have done. And now we have the province of Barcelona with the city of Barcelona with a river. That's super simple, but this idea you can extend it to anything. Okay. Any question? Yes.
Maybe you are going to explain us later that, but there's any tool that allows us to draw these polygons instead of typing the coordinates?
Yes. QGIS. QGIS. The one that I showed before. With this one, you can create this lines, and I guess you can create polygons. I mean, I don't use it that much, but I know you can use it with this QGIS. QGIS.
So you save, so you draw whatever you want, you save it as GeoJSON and you load it.
Yep. The same way that we did, we created the triangle before. This triangle we didn't create it with Shapely. It came from a GeoJSON. I mean, I created it and I created it with Shapely, but I could have done it with QGIS.
Otherwise, you have to implement a backend that, imagine that you have a map and you want to draw on that map and store, for example, a parking lot.
Yeah.
You have to implement that backend and that stuff, no?
Exactly. That's, for example, something that we did in our startup. We can create some random polygon. This is a feature of Mapbox, and with this area we can store it. I think we can save it, and this is saved. I mean, we don't save a GeoJSON. We save the vertices, because usually when it's human, someone has created it. It's not such a difficult polygon that we can't save in the. But that's a good idea to have a backend to do that. Mm-hmm. Any other question? Okay, then we are going to jump to the second part. There's 10 minutes left now. I think we can use them and then have a small break. So please go to Moodle and download the second part, upload it to Google Drive, and open Geoprocessing Application Students. And then run the first 5 cells. So we have GeoPandas and Matplotlib and Google Collaborative Drive Mount. Okay, do you have it? Not yet. Okay, so in this notebook, what we are going to learn is 10 different functionalities that are very useful when working with geospatial data, geographic data. So this is not data science. This is just geographical manipulation of data. So first, we are going to load this file, which is one area. somewhere in the world, and we can plot it. This area, this is not Spain. This is, who knows. Then second area, this is also, it's very close to the other one, and a river. And then if we plot all of them, we can see, it's very big, sorry. We can see that they overlap. Okay, so we have first area is the one on the top, second area is the one on the bottom, and the river overlaps both, and the areas are also overlapping among them. So the first thing that we are going to do is that we want to get the area that is overlapping both. For that, we are going to use the overlay function with the how attribute in intersection. We overlap both, and let's see what happens. We get the area in the middle. Okay? Is that clear? We are getting this area in the middle. Can you see it? That's the first function. Intersection, that's the name of the function. Getting the intersection of two overlapping areas. If they don't overlap, well, I don't know what happens if they don't overlap. But if they don't overlap, probably we will know. One, either because it raises an error or either because it's empty. Both are okay. Second, okay, I would like to have only one polygon defining all the outer region and not having two polygons overlapping. Just create one polygon with all these two areas, right? This is called the union. We do the same overlay with the how union. And we can plot it. But what is the problem with union? Oh, well, it's not a problem. It's just a feature. We still have the first polygon, the second polygon, and now we have the third polygon. So we have all of them. If we take a look at the resulting data frame, we have 3 rows. First polygon, second polygon, and the third one, which is the intersection. Okay, so with the union, you can get the intersection if I lock the first one, or you can get all of them, independently, right? So with this one, you can get almost everything that you may want to do. That was the third function. What if I want to delete the area that is in the middle? They are overlapping, and I don't want them to overlap anymore. That is called dissolve. Okay. Oh, sorry, I was mistaken. What if I want to mix them? Sorry, in only one polygon? That is called dissolve, right? Sorry. So if we want to have only one polygon, we have to union it and then dissolve it. If I wanted to create the territory of Spain using all its provinces, then I will have to union all the provinces and then dissolve them, for example. And then, where I was mistaken, if I want to remove the intersection, that is called the symmetric difference, and you can see we will remove the central part, right?
So
yes.
Symmetric difference, you have 2 polygons or 1?
2 polygons. Look. You can get the same with the union if you just remove the intersection. Do you remember the union had this 3? So if I get 1 and 2, then it's the same. We are all the time doing almost the same thing, but yeah, we have to know them because they are useful. Okay. And now we can take the difference between the polygons. That is only the polygon that doesn't overlap with the other one. Okay, so if I take the difference with the first one with respect to the second, then I get this part, which would be the same idea of getting this only this row. And if I get the difference between the second and the first, then I get the second one, which would be exactly the same as getting this polygon here. If I lock it and I get the index one. I know this part is a bit boring, but now it gets more intense. Actually, we are going to break here because the buffer and the centroid and these other things, I think we need to be a bit fresh. Okay, is that clear? All these simple functionalities that GeoPandas has inbuilt. Any other question? I think it's quite straightforward. Okay, so let's break a couple of minutes. Function that we are going to take a look is no longer related to overlapping geometries. In this case, we are going to take a look at buffering, that is filling, creating area out of something that doesn't have an area, like a point or like a line. So if I have a point that is a non-dimensional singular point, a buffer would create an area around it, so I can determine the radius. So buffering something means creating area. Okay, if I buffer a point, it will create a circle. If I buffer a line, it will create a rectangle. If I buffer a polygon, then it will grow. And why is this interesting? And that's something, because I didn't tell you something, but I will give you some homework for the next day. So in this homework, you will have the Spanish territory and you will have the some points. And these points are going to represent something different. But if I want to know what is around this point, I will have to buffer it, and then I will have to filter what is around. For example, if I want to ask, this point, which is in Madrid, is it close to the frontier, to the border with Castilla-León, or not within the 500 meters? Then what you will have to do would be create an area and then filter out. And then if it touches this other polygon, then you can claim that, yes, this is true. It touches the border. If it's in the center and it doesn't, then it doesn't touch the border. So it's very useful in that sense. Did you understand what I mean? So the way we can perform this operation is by using buffer, okay? Buffer from the GeoPandas. It's a function, inbuilt function, but it's very important to have, again, I pay attention on that, is that the CRS should be the correct one. Because if I want to create a buffer of 500 meters, then the CRS should be in meters, the units, because otherwise, if I create a buffer of 500, but it's latitude, longitude, then I will create a buffer that is bigger than the size of the Earth. Okay, because 500 points of latitude, I mean, we have 360, so that's even bigger. Okay, so if we take a look, I've buffered the river, then the river is going to have, then the river is going to have area. It's no longer a line, it's a two-dimensional polygon. Okay, that's very important. Now it's a polygon. Now I can operate the same way we have been doing with this, because now it's a polygon. Now we have area. And the same idea for plotting a point. Okay, this is what happens if we don't change it. Okay, the river doesn't make any sense. So if we create a point, this point in the middle of nowhere, in the 0, 0 latitude, and then we buffer with 1, then we create a circle. That's exactly the same idea. Yes, this is coded. This is what I wanted to show. And what is the area? Pi, of course, because it has radius 1. So if I put it in a geodata frame, I can do a point which is radius 50. So the area, again, it's this, which is okay, with some, because we have more precision on pi. Okay, is that clear what the buffer is and how we can use it in the real problems? Because this is very important for the exercise later. You'll see. For example, another example. This is a way we could know if an antenna that is spreading, that we have a signal from 5 kilometers, we can know if it's reaching houses somewhere or not by buffering a point. Okay, I won't continue in this idea, but if you have any question, you can ask. Now, the next operation, or the next idea that we can do is to compute the centroid. The centroid is the center of mass of a polygon. We only have centroids in polygons. So the centroid of this polygon is here. If I create this polygon, the centroid is outside, but that can happen. Okay, that's important. But it's the center of mass. And why is this useful? Because sometimes working with a polygon could be a bit heavy. Maybe this polygon, it's very difficult. It's a very difficult polygon. And it could be enough with working with one point. Maybe this is the shape of a hill, but I just want to point out that there is a hill there. So I don't need to work with the polygon. I can compute the center of mass and say hill. Only 0-dimensional, 2 latitude and longitude, not n latitude and longitude points with the polygon. Okay. That's why this is very useful. This is almost the opposite. In this one, we were creating area, and with this one, we are destroying area. We don't have any area anymore because we have a point. Okay. So again, it's a built-in function, centroid. It's not even a function, it's an attribute. So we can plot it, and we have computed the centroid of the union, that is the three areas that we had, one on the top, one on the middle, and one on the bottom. So I think if I plot it all together, I think it's here. Oh yeah, you can see we have the center of mass in the center of the polygons. Yes?
Should we this time ignore the word means when creating the union of centroid?
Never.
But this time works.
Oh, sorry. I don't know what, probably because union. Wait. Okay. It says that we are using a geographic CRS, that is latitude and longitude. Probably centroid works better with meters. I didn't know that. And I don't know why. If I'm but apparently it worked. So we shouldn't ignore it, but I will research why, because I don't know. Okay, I think this is like again talking about the same idea. We have finished with all the functionalities that I wanted to show in the data frame. This is an example of the things that we can do. For example, we can load the airports in the United States. There they are. And this time we don't have any geometry. This is a data frame in which we have latitude and longitude. This happens a lot in the real world. So we need to convert it to geodata frame. How do we do that? We can create a point for each of the latitude and longitude. And now that this point is a geometry, we can introduce it as the geometry field of the geodata frame and create a new geodata frame. I repeat, we had a normal data frame and someone put the latitude and longitude columns. But we can't work with this latitude and longitude. We need to work with the geometry. We need to work with geodata frame. So we convert this latitude and longitude to point using Shapely, and then we create a geodata frame. Now that we can do everything that we have seen already. Plot it, dissolve it, create buffering or whatever. Another thing that is very common is that instead of having latitude and longitude, what we have is an address, a street name. And for that, we use what is called the geocoding. This is a much difficult geocode, much difficult functionality. It's not like creating a point. It's something that we need to use external service to geocode something. Geocode for free API. I usually use, let's ask a Stack Overflow, Nominatium, this one, which is part of OpenStreetMap. Do you remember OpenStreetMap? The free Google. So they have this tool. You can pass any address in the world and it will return a point, latitude and longitude. And that's very common. But the problem is that this doesn't work that well, these days at least. Google is still much more powerful in this, in geocoding. So if you want to do something that is for a client or for a business, OpenStreetMap doesn't work very well for now. Just for you to know. But that's another. I can't have an example because this is, we have to create a server. We have to call this server with the address. It's something a bit out of the scope of just using a Google Collaboratory, but just for you to know, okay? Then another thing that we can do, exactly the same as we can do with normal pandas data frame, is joining data frames. Now I have the state names. It contains the state names and the code names. This is the United States, okay, Alabama, AL, Alaska, AK. And I can join it with the airports based on the state code. So now I have a new data frame that has both information, the airport and the name of the state. This is something that we know from data frames, from pandas. But a very cool thing is that we can do exactly the same, but with the spatial information. That is, how would you join, instead of based on the name of the state, based on where the airport is located within a state? that is called a spatial join. And that's also very common to use, because instead of joining two data frames on one column name, we join them based on the geography, the geometry. So we have the states again. Now we are going to plot it. There we are. And now we have the airports. Let's plot it together. This is where the airports are located, some of them in the States. And what we wanted to do is we joined them, intersecting only a couple of them. Okay, so using the intersect operation, we found where this airports that were in the States, because I'm sorry, I'm not sure if this is wrong data actually. Okay, imagine that these airports are worldwide, all the airports in the world, but I want to get only the airports in the States. Then I would join these two data frames, but a spatial join. That is only the airports that intersect the geometries. Then I would get the airports that only exist in the geometry of the United States. Okay, is that clear? Because I feel that there's some kind of problem in this picture. So instead of joining two data frames based on a column, we join them based on the geometry. It's very similar to intersecting, just intersecting. But now we have all the information that we had in this data frame, in this one and this one. So the name of the airport, the name of the state, they are joined, but based on the geometry. Is that clear?
Does it have a tolerance, or is it just exact to the precision of the machine?
In this case, it's exact. You can set tolerance with different operations. Also, you can do something that is S-join, spatial join, nearest. That is, they don't need to be in the same overlapping, but getting the nearest one. That is very useful when you're working with streets, and I want to know which shops are the nearest to this street. So I S-join nearest with the, yeah. So I get the shops that exist in that street, and I don't need to buffer it. I just S-join nearest. Mm-hmm. Is that clear? That was a bit difficult concept. Any other question? Okay.
I don't understand why the command line just, for example, in Florida, there are no airports.
Yeah. I'm sorry, that's my fault. I'm not sure why, because that's what I saw when I saw the picture, and I'm not sure why. But I can send you. I will send a message in Moodle when I fix it. Okay, because I'm not sure why. Let's see another example. We have the Spanish provinces, and I'm going to create a random set of points over Spain. Puntos. We plot it. These are the random sets of points over Spain. We can plot them together. Okay. And with the S-join, what I'm going to do is to filter out the provinces that doesn't have any point. Wait. Yeah, for example. That's another idea. So imagine that these are the airports or whatever. These points mean anything. So when we don't have any point, we don't want to see it, and we don't want to get that rows in our data frame. That's what we are doing. with the spatial drawing. Okay. And you can change it to, this is inner, but if we get left, then we are going to get all the provinces, but where there exists no point, then there's going to be a none or no information there. No points. Exactly the same as in a normal merge join between two data frames. If we do the opposite, we get all the provinces, but all the points, and where we don't have any province, it's a none. Where we have a province, it's a well, the same idea as a merge, okay, but with the spatial information. Okay, so we're finished with the functionalities of GeoPandas, the basic functionalities. Is everything clear? I will send a message on that because I'm not sure why that happened, but I will solve it. So we are going to do jump to the next collaboratory, which is very short. You have to download the part 3 from Moodle, then upload it, then run the first 5 cells. In this one, we are going to take a very quick view to Plotly. Okay. So Plotly is a library. The idea, what I like about Plotly is that you can get an HTML file directly when you compute a graph, and we can. It's more or less interactive in the sense that you can hover over it, and it will give you some information. You can zoom in, you can zoom out, you can pan, do whatever, right? That's why I like it. This is random data, but it also works with maps. So Plotly with interactive maps. In this case, I'm querying one of the Plotly data sets. Okay, that's why we are not loading anything. But this is what we get. It's countries in the world and the population and the life expectancy. And we can take a look, and we get a map that it's interactive in the sense that I can hover over the countries and know some information. I know the United Kingdom has 60 million people, Spain 40 million, at least in this year, 2007, Italy, Algeria, Nigeria, Brazil. Okay, that's why I like it. And then, if you recall, I mentioned before this weird word, choropleth. What does it mean? Well, it's nothing but colorizing the map with a CMap, with a gradient. That is, for example, in this case, that we are going to take a look at the states of the United States, they are going to have a different color depending on certain attributes. In this case, the unemployment rate. So the lower is going to be darker and the higher is going to be lighter. So apparently in these counties it's higher and in these counties it's lower. The idea of a choropleth map, which is very simple, is that in a very quick site we can get all this information, and if I want to know a bit more, then I can hover over it and then I will get the information. I'm showing this for you to have an example of what we can do, and because I would like you to explore a bit more this library or any other one in the exercise that I'm going to give to you as a homework. Okay, but very quickly, I'm not going to get in much detail on this, unfortunately, but 12th of April, I will. All right. Any question about visualization? This was very quick. I mean, no much details. Okay. Then. And that was everything. Thank you. We finished. Really? Oh, wow. Gracias.